Good morning everyone. My name is Siddharth Muralidharan and my student ID is 5378370. My topic for today's Engineering 851 Assessment Task 3 is removal of pharmaceutically active compounds and enzyme disrupting compounds from wastewater using activated carbons. So before we get into the actual topic, so let us get an introduction of what are pharmaceutically active compounds. Pharmaceutically active compounds are the pharmaceuticals that get introduced into the wastewaters due to the therapeutic drugs that are consumed by the human bodies. Now, if you look at the basics, once the medicines are ingested by the body, it is metabolized in the liver and it is excreted in the form of urine and feces. So this is the method in which these organics, these compounds get introduced into the wastewaters. There are, for example, I would like to. The examples are carbamazepine, which is used in the treatment of seizures, and ibuprofen, which is used in the treatment of fever as well as pain. So the reason of why these have to be removed is just because of the fact that these compounds can trigger a lot of adverse reactions. Even in normal person, if he consumes it, there can be a lot of adverse reactions, and the need to remove these compounds is a big necessity. The next aspect is EDCs. EDC stands for enzyme disrupting compounds. Now, what are enzymes? Enzymes are basically biocatalysts. These actually trigger various responses in the cellular level. So the basic mechanism by which enzyme works is enzyme attaches with the cell membrane and it introduces a cellular response. So basically, for example, if we take a food, so if it goes to the stomach and that food acts as a stimulus in the production of insulin. So that production of insulin is a cellular response. So similar to that, there are many enzymes that causes several cellular response. And enzyme disrupting compounds are the man-made compounds or the artificial compounds that mimic or antagonize the effect similar to what an enzyme produces. So that this is one more need in which these compounds needs to be removed from the wastewater, because if it is introduced into the drinking waters and a healthy person drinks it, and these compounds can trigger a lot of reactions. For example, many pesticides and pharmaceutical products can trigger a lot of adverse reactions, as discussed earlier. So the next part is activated carbon. Activated carbon is a material that can be produced from almost anything which has a high carbon content. Now, an activated carbon works basically because it works on a principle of adsorption, and now adsorption is a surface phenomenon. So this is the actual structure of how an activated carbon looks. An activated carbon has pores and micropores in which compounds can be trapped. So this is the mechanism in which activated carbon works. Now the major parameters that play crucial role in the adsorption are surface characteristics like pore distribution and surface groups. Any material can be converted into an activated carbon either physically or chemically. Physically by thermal degradation or chemically by using several chemicals. So when these are activated, the pore structure or the surface structure of the material itself changes. There are a lot of pores that are formed, and these pores actually play a crucial role in the removal of these micropollutants or any other compounds for that matter. As I mentioned, activated conditions play a crucial role in the formation of several surface characteristics like pore distribution and formation of surface groups. So why are PHACs and EDCs have to be removed from the wastewater? So as discussed in the earlier they play a crucial role in the regulation of metabolism of the body. So they can trigger a lot of adverse reactions if they are consumed by a healthy person. They mimic or antagonize natural hormones. Now these compounds are detected in surface waters, wastewater and runoff and landfill leachates. Now why are they detected in these waters like surface waters? They are not supposed to be present in these waters like surface waters and drinking waters. They are not supposed to be present. So why are they present? The reason is that the present wastewater treatment plants are not efficient enough in the removal of these micropollutants. So that is where activated carbon plays a crucial role. Several studies have been performed and activated carbon has proved to be a best adsorbent among the many of the things. One of the example I would like to bring over is a coconut shell based activated carbon was compared with two more adsorbents, two carbonaceous resins in the adsorption of these pharmaceutical active compounds and EDCs. And it was observed that coconut shell based activated carbon was efficient was more efficient than the other two adsorbents. And one more example is that activated carbon prepared using eucalyptus sawdust, coffee grounds, calcium hydroxide and soybean oil proved to be one more form of an activated carbon that is efficient in the removal of these compounds. Now if you look at this, the materials used to make an activated carbon are naturally available. They can be waste which can be generated, which can be converted into activated carbon. So that is one of the advantage of using activated carbon as a process in the wastewater treatment plants. So again, one more experimental adsorption conditions. pH of the solution also plays a crucial role in the treatment using adsorption as a treatment plan, as a treatment step. The dosage. So there will be a number of micropollutants that will be present in the wastewater. So the amount of adsorbent or activated carbon that we put into the water also plays a crucial role in the extent of removal of these compounds, and as well as the physico-chemical properties of the target compounds. The target compounds being EDCs and PHACs, they differ with physical and chemical properties, and the way they get adsorbed also depends upon these properties. So the research question I am addressing to is, which combination of experimental conditions like solution pH, sorbent dose and contact times suits best for the effective removal of PHACs and EDCs using biochar, which I will be discussing in the next slide, using spent leaves as an adsorbent. Now why did I choose spent leaves? Spent leaves is the tea leaves after you get the tea bags. So after you use this tea bags, so these tea bags are a kind of a waste that can be reused. So the amount of waste generated is over 300,000 tons per year. So that the availability of the raw material is more, and the waste has, instead of being disposed, it can be used for this particular purpose. And yeah, the same thing. And research has been done, and spent tea leaves has been proved to be an efficient absorbent in the removal of textile industry, drugs and heavy metal compounds like arsenic and zinc and lead. So my research question actually targets like whether spent tea leaves is efficient in the removal of pharmaceuticals as well. So my research design. So before we get to that, what is a biochar? Biochar is basically a material that is heated in an oxygen limited environment. So that any material that is heated in an oxygen limited environment is called a biochar. So the first step in which my research design will proceed is, first the tea leaves are brought, the spent tea leaves are brought and they are washed using distilled water several times in order to remove the soluble compounds, and they are oven dried at 50 degrees Celsius for 20 hours to remove the excess moisture. In order to maintain uniformity in the particle size, they are sieved using a mesh size of 600 micrometer. Now in this particular my research design, I developed two varieties of activated carbon, biochar basically, NSTL and OSTL. NSTL stands for nitrogen spent tea leaves and OSTL stands for oxygen spent tea leaves. Both of these are heated at 450 degrees for 6 hours. The difference being NSTL is heated under pure nitrogen, and OSTL is heated at 5% oxygen and 95% nitrogen. So the difference here is the amount of oxygen is limited in both of these things. So that leads to the production of biochar. So these are the target compounds that I am using in the analysis of my study. 4 PHACs and 3 EDCs basically. These solution compounds, the solution compounds will be dissolved in ultra pure water at a concentration of 10 milligram per liter. So batch experiments will be conducted using 100 ml glass of conical flasks. A control, basically, in order to compare the effects of the adsorbent that I develop, I use a control that is a commercially available activated carbon Darko 242233 as a comparison in order to test the results, and a blank. And in order to optimize the pH, the solutions, the 10 milligram of each biochar will be added into 14 conical flasks under pH ranging from 1 to 14 at 25 degrees Celsius and stirred magnetically for 4 hours. So here, as you can see, only the pH of the solution varies, except the concentration, the dose and the temperature remains the same, and even the contact time remains the same. So you can analyze, after conducting this particular part of the experiment, you can analyze which particular pH is efficient enough in the removal of these micropollutants. So in the next part, I am analyzing the sorbent dose. So in this, only the sorbent dose changes, and 50 ml of target compounds is taken, and it is stirred at for 6 hours at 25 degrees Celsius and neutral pH. So in this, the only component that is changing is the sorbent dose. The same thing is done in contact times. Keeping the contact times as varied, the rest of the parameters are kept constant, so that you get to know which is the best contact time in the expatient removal. So the analysis will be conducted using chromatographic methods developed by Notsoukalas et al. Solid phase extraction and usage of these particular devices will be used in the analysis of the target compounds that are removed. So the limitations of my research design is that standard operating conditions are followed, and this is a big disadvantage, because in the actual wastewater treatment you cannot actually maintain all these operating conditions as desirable. And this particular research design ignores the effect of other trace micropollutants in these. And taken into consideration only, this particular research design is taking into consideration only 10 target compounds, leaving behind several other compounds, and whether or not they are adsorbed properly or not, it is not discussed in this particular research design. So my conclusion is that spent tea leaves can be used as an adsorbent in the removal of the previously mentioned discussed PHACs and ADCs, because as spent tea leaves is is available in large quantity, and it is more cheap as well. So use of spent tea leaves in the in the removal of these micropollutants like pharmaceutical active compounds and enzyme disrupting compounds is useful enough So that is what I would like to conclude, and thank you for your attention.